Hello everyone, myself P. Jithendar, Assistant Professor in Electrical and Electronics Engineering, MLR Institute of Technology. In today's video session, I am going to discuss about the torque equation of three-phase induction motor. Right? So here, previously we have discussed about the torque equation of DC motor, that is 0.159 into 5Ia Zp divided by A. So in that case, torque is always directly proportional to phi into Ia. Phi is flux, Ia is the armature current, right? So now in today's class we are going to discuss about the torque equation of three-phase induction motor, right? So here the torque equation of three-phase induction motor. So here generally torque is nothing but it is the product of force and radius, right? So from that we'll get torque is always directly proportional to phi I. In generally, torque is always directly proportional to product of flux and current, phi into I. If it is a three-phase, so T directly proportional to rotor flux phi R, rotor current IR, and power factor cos phi R. So here torque is always directly proportional to phi R, IR and cos phi R. Phi R is the rotor flux, IR is the rotor current, cos phi R is the rotor power factor. Okay. So here in induction motor, basically we are having the two main parts, that is stator and another one is rotor. So stator and rotor, right? So these are the rotor flux, rotor current and power factor cos phi R, right? So here this equation we can also write like this. The rotor EMF is always directly proportional to rotor flux. So ER is always directly proportional to phi R. So generally we know the EMF equation here E equal to phi ZNP divided by 60A. So in this equation phi ZNP by 60A is the constant. So then E equal to some K into phi. So this equation we can write E directly proportional to phi. Or we can also write the rotor EMF is always directly proportional to phi R. The rotor EMF is always directly proportional to rotor flux phi R, right? So here I am taking the ER directly proportional to phi R. Now substitute this ER value, this phi R value in this torque equation. So this rotor EMF I am writing like this, E2 into IR cos phi R. So E2 into IR cos phi R, right? So here now in this equation we have to calculate the rotor current IR and rotor power factor cos phi R. We need to find out the rotor current IR and cos phi R, right? So here the rotor current, generally I equal to V by R. So according to Ohm's law, the current equation I equal to V divided by R, right? Suppose if it is a AC, so I equal to V divided by Z. So for the induction motor, the rotor current I am writing like this, rotor current IR is equal to rotor EMF ER divided by rotor impedance ZR. So like this I am writing the equation. So therefore the rotor current is equal to rotor EMF divided by rotor impedance ZR. So here the rotor EMF is always depends on the slip of the induced EMF, that is S into E2. S into E2 is the rotor EMF produced by the rotor, that is ER is equal to S into E2. So ER value. Now how we will get ZR value? That is from the Pythagoras theorem. So from the Pythagoras theorem I am taking a triangle here. This is O, A and B. and here I am taking as a ZR, rotor impedance, and this is rotor resistance R2, and here is the reactance X2, S into X2 rotor reactance. Okay, so now, so this is 90 degrees, and here is the phi r, cos phi r, right? Now from the triangle OAB, I am writing like this: AB square equal to OA square plus OB square. So from the triangle OAB, AB square is equal to, that is AB square is equal to OA square plus OB square. What is AB here? ZR square equal to, what is OA? R2 square plus what is OB? S into X2 whole square. Now this ZR I am writing like this: ZR is equal to under root of R2 square plus S into X2 whole square is the rotor impedance, right? Here let us take this as equation 1, this is equation number 2, this is 3, and this is 4. Now we can substitute equation 3 and equation 4 in equation number 2. So here substitute equation 3 and 4 in 2. So here the second equation, rotor current is equal to rotor EMF divided by rotor impedance ZR. So the rotor EMF is S into E2 divided by rotor impedance. So rotor impedance is under root of R2 square plus S into X2 whole square is the rotor current equation. IR equal to S into E2 divided by under root of R2 square plus Sx2 whole square. So let us take as this is equation number 5. So here in this equation IR is over. So IR is equal to SE2 divided by under root of R2 square plus Sx2 whole square, rotor current. Now I need to calculate the cos phi r. I need to calculate the power factor cos phi r. So from this triangle OAB, so cos phi r equal to, so from the triangle OAB, cos phi r is equal to OA divided by AB. So OA divided by AB, that is equal to OA means R2, AB means ZR, that equal to R2 divided by, where ZR is equal to under root of R2 square plus Sx2 whole square. So under root of R2 square plus S into X2 whole square is the rotor power factor cos phi r. Right, here let us take as equation number 6. Now we can substitute equation 5 and equation 6 in equation number 1. So now we have to substitute equation 5, equation 6 in equation number 1. So now equation 1 is T directly proportional to E2 IR cos phi r is the equation, right? So now T directly proportional to E2 into, so rotor current, what is rotor current? S into E2 by under root of R2 square plus Sx2 whole square. So here S into E2 divided by under root of R2 square plus Sx2 whole square into power factor cos phi r. So where cos phi r is R2 divided by under root of R2 square plus S into X2 whole square. Right? Now by using this equation, T directly proportional to S into E2 square R2 divided by, so under root of R2 square plus Sx2 whole square, again square, so square root get cancelled, then T equal to some constant K into S into E2 square R2 divided by R2 square plus Sx2 whole square. So here we are having one constant here. So that constant I am taking as 3 divided by 2 pi ns into S into E2 square R2 divided by R2 square plus S into X2 whole square is the torque equation of 3-phase induction motor, where here ns is nothing but synchronous speed. So ns equal to 120f divided by p is the synchronous speed. So this is the torque equation of 3-phase induction motor. So T equal to 3 by 2 pi ns into Se2 square R2 by R2 square plus Sx2 whole square. Okay, here is the torque equation of the 3-phase induction motor. Okay, so in this torque equation we will discuss some problems here. So here we are having the one problem. So a 3-phase 400 volt 50 Hz 4-pole induction motor has star connected stator winding. Okay, so before that we will discuss one point here. If it is a star connection, what is the relation between the voltage and what is the relation between the current? In star connection, in terms of voltage and phase, line voltage is equal to root 3 times of the phase voltage is the relation between the line voltage and phase voltage if it is a star connection, and current relation is line current is equal to the phase current in star. Suppose in delta, if it is a delta connection, in delta, so reverse of this, so line voltage is equal to the phase voltage and line current is equal to the root 3 times of the phase current. Okay, so here you have to remember this star and delta. In star, the line voltage and phase voltage relation is VL is equal to root 3 times of the phase voltage. In terms of current, line current is equal to the phase current. If it is a delta connection, line voltage is equal to the phase voltage and line current is equal to the root 3 times of the phase current. Okay, so now a 3-phase so a 3-phase 40 volt 50 Hz 4-pole induction motor has star connected stator winding. The rotor resistance and reactances are 0.1 ohm and 1 ohm respectively, and the full load speed is 1440 rpm. Now we need to calculate the torque here. Okay, so here first of all we need to write the given data first. So here a 3-phase 400 volt 50 Hz. So if it is a star connection, VL is equal to root 3 times of the V phase. So V phase equal to VL divided by root 3, that is equal to, so VL means 400 is given, so 400 divided by root 3 phase EMF, and frequency F is equal to 50 Hz and total number of poles P equal to 4 pole. Induction motor has star connected stator winding and the rotor resistance R2 and the reactances are 0.1 ohm and the reactance X2 equal to 1 ohm respectively. The full load speed is 1440 rpm. So NSC is equal to 1440 rpm. So 1440 rpm. Then we need to calculate the torque. So torque of the 3-phase induction motor. Okay. So here the torque equation is T equal to 3 divided by 2 pi ns into S into E2 square R2 by R2 square plus Sx2 whole square is the equation. Okay. So now that is equal to, so 3 divided by 2 pi ns. So ns is 1440 rpm into, so S value. So here we need to calculate the S value. So how we can calculate the S value? So see, so already we know S is equal to ns minus nr divided by ns is the equation. So where ns equal to 120f by p, that equal to 120 into frequency. What is frequency? 50 Hz. By total how many poles are there? 4 poles. So 4 threes. That is equal to 1500 rpm. Now calculate slip. So S is equal to ns minus nr divided by ns. So here they are given rotor speed, that is nr. So nr is equal to 1440 rpm. So that is equal to ns is 1500 minus 1440 divided by 1500. That is equal to, so something will get 0.06 is the S value. Now substitute all the values in this torque equation. So then T equal to 3 divided by 2 pi into ns, 1500 into slip value 0.06 into, so rotor EMF, this is rotor EMF, that is E2. So 400 divided by root 3 whole square into R2 rotor resistance 0.1 divided by R2 square plus Sx2 whole square. So R2 means 0.1 whole square plus S value 0.06 into X2 value 1 whole square. So here by solving this equation we'll get some 35.6 Newton meter is the torque equation of the 3-phase induction motor. Okay. So here you have to remember this. If it is a star connection, what is the relation between the line voltage and phase voltage, and what is the relation between the line current and phase current? If it is a delta connection, what is the relation between the line voltage and phase voltage, and what is the relation between the line current and phase current? Okay. So here is the torque of the 3-phase induction motor, right? So we'll go for the next problem. So here a 3-phase 50 Hz 400 volt induction motor has 4 pole star connected stator winding, and the rotor resistance and reactances per phases are 0.15 ohm and 15 respectively, and slip is given that is 5%. So we need to calculate the torque. So here first we have to write the given data here. So frequency is there. So frequency F equal to 50 Hz and 400 volt induction motor has 400 poles, stator, connected stator winding, and the rotor resistance. So all are in phase. So the rotor EMF is equal to 400 volts and total number of poles are P equal to 4. So star connected stator winding and rotor resistance R2 0.15 ohm and rotor reactance X2 1 ohm respectively, and the full load slip S equal to 5%, means 5 by 100, that equal to 0.05. Then we need to calculate the torque of the 3-phase induction motor, right? So here torque is T equal to 3 by 2 pi ns into SE2 square R2 by R2 square plus S into X2 whole square. But here we need to calculate the ns value. So ns is equal to 120F by P, that is equal to 120 into frequency is 50. So total poles are 4. So 4 threes, that equal to 1500 RPM. Now substitute all the values in this torque equation. So we'll get T equal to 3 by 2 pi ns, that is 1500 into S value. They are given S value, that is 0.05 into E2 400 square into R2 0.15 divided by R2 value. So R2 value is 0.15 whole square plus S 0.05 into X2 value. So X2 is 1 whole square. So here by solving this entire equation, so we'll get 175.8 Newton meter is the torque of the given 3-phase induction motor when we are giving the 400 volt AC supply, right? So here is the torque equation and problems on the torque equation. Okay, so in next class we are going to discuss about the torque slip characteristics of 3-phase induction motor. So thank you one and all.